Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is the capacitor charging process. Our objective is to examine the transient or time-based analysis of the capacitor charging process. We'll learn capacitors experience a brief surge of incoming current, where the duration and intensity of this brief current surge is determined by the electrical properties of the circuit under inspection. Additionally, we'll learn that during this transient charging process, voltage across the capacitor rises to a steady state value and then stabilizes. Later lectures will examine the capacitor discharge process and increasingly sophisticated capacitor charge and discharge scenarios. This lecture operates under the presumption the viewer is intimately familiar with exponential functions as illustrated in the exponential functions lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Additionally, I need to make it perfectly clear that all those skills we developed during the course of our earlier study are still valid and still absolutely necessary. Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, basic series properties, basic parallel properties, and Thevenin's theorem are still true and will always remain true, and at no point will they not be true. You need to have these skills sharp and at the ready at all times. If you are less than qualified or less than confident in the use of these electrical theories, by all means, please take advantage of these lectures at the Basic Electronics 1 DC Circuit Analysis playlist, available at the Big Bad Tech channel. If at any time you need to revisit or review these topics, that option is available and encouraged. This content assumes you know these skills and will not go into unnecessary detail deriving nor explaining any conclusions drawn by these base techniques. Long story short, the transient analysis of reactive devices like capacitors and inductors is not for the weak, lazy, and ugly, and only the most intelligent, motivated, and sexy among you will survive. Assuming you're still with me, let us begin. There's a couple ways to explain the transient or time-based analysis of the capacitor charging process. However, the best method I found is to view the process as three sequential phases: the initial conditions, the final or steady state conditions, and the transient process, representing the brief transition from the initial conditions to the final steady state values. From the beginning, think to the end. Given identifiable start and end points, all we have to do is figure out how the process behaves in between these boundaries. The general purpose plots of current through the capacitor and voltage across the capacitor as functions of time illustrate the simple capacitor charging process quite nicely. Consider the initial conditions. Uncharged capacitors initially experience a momentary surge of current. Voltage across an initially uncharged capacitor starts at 0 volts. Consider the end state. Current flow through a fully charged capacitor eventually stops. Voltage across a fully charged capacitor eventually stabilizes at some constant voltage. In between these initial and final conditions, current through the capacitor and voltage across the capacitor don't instantaneously change, but rather undergo an exponential transition. Don't make the transient analysis of the capacitor charging process hard. Current through an uncharged capacitor experiences a brief high surge and decays to 0 amps. Current through the capacitor as a function of time can be modeled using the general purpose decay function, where IC of t equals I times e to the negative t over tau, where capital I is the magnitude of initial current surge and tau is the time constant. Voltage across an uncharged capacitor starts at 0 volts and grows to some steady state final value. Voltage across the capacitor as a function of time can be modeled using the general purpose growth function. Vc of t equals Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial voltage and Vf is the final steady state voltage and tau is the time constant. If the capacitor happens to be initially uncharged at 0 volts, Vi equals 0 volts, and the general purpose growth function resolves itself into Vc of t equals Vf times 1 minus e to the negative t over tau. Two convenient models define the start and end points. Initially uncharged capacitors at t equals 0 can be modeled as a short circuit. Fully charged capacitors, in contrast, after t equals 5 time constants can be modeled as an open circuit. I say again, initially uncharged capacitors can be modeled as a short circuit, and after 5 time constants have elapsed, fully charged capacitors can be modeled as an open circuit. These models can be used to determine the magnitude of the initial current surge and the final steady state voltage obtained across the fully charged capacitor. Given these convenient models, really the only data point we're missing for transient analysis is the time constant tau, defining the rapidity of this transition. Luckily, this property is also easily calculable. The time constant tau for a simple series capacitor charging circuit is the resistance value in unit of ohms times the capacitance value in units of farads. Too easy. Consider this simple series circuit consisting of a 12-volt DC power source, an open switch, a 200 ohm resistor, and a 15 microfarad capacitor. Let's assume the capacitor is initially uncharged and exhibits no voltage differential across it. VI, initial voltage, therefore equals 0 volts. The time constant for this simple series circuit is the resistance value times the capacitance value. Substituting given values of 200 ohms and 15 microfarads, we obtain a time constant of 3 milliseconds. The moment the switch is closed, let's say we start the clock at t equals 0. At t equals 0, the initially uncharged capacitor can be modeled as a short circuit, a low resistance path through which substantial current will flow. Using this simplification, our initial condition can be modeled as a 12-volt source in series with a closed switch, a 200 ohm resistor, and a short circuit with no resistance. This means the only element controlling current in this circuit is the 200 ohm resistor. Ohm's law demonstrates that the series circuit experiences a brief surge of 60 milliamperes of current. This is the start value for current as a function of time. Again, voltage across the initially uncharged capacitor is 0 volts. After 5 time constants, in this case 5 times 3 milliseconds or 15 milliseconds, the fully charged capacitor in contrast can be modeled as an open circuit or infinite resistance path through which no current will flow. Using this simplification, our final steady-state voltage obtained across the fully charged capacitor will be 12 volts. This is the end value for voltage across the capacitor as a function of time. Current through the capacitor will be 0 amps. We now have the start point, the end point, and the time constant for these properties. Current through the capacitor as a function of time could be modeled as IC of t equals 60 milliamperes times e to the negative t over 3 milliseconds, where 60 milliamperes is the magnitude of the initial current surge and 3 milliseconds is the time constant tau. The plot of current through the capacitor as a function of time demonstrate it initially spikes to 60 milliamperes and then drops to 0 by 5 time constants, or 5 times 3 milliseconds, or 15 milliseconds. Voltage across the capacitor as a function of time can be modeled as Vc of t equals 12 plus 0 minus 12 times e to the negative t over 3 milliseconds, where 0 volts is our initial voltage value, 12 volts is the final voltage value, and 3 milliseconds is the time constant tau. If we remove the superfluous initial value of 0 volts and factor out the 12 volts, Vc of t resolves itself into a much simpler 12 volts times 1 minus e to the negative t over 3 milliseconds. The plot of voltage across the capacitor as a function of time demonstrates it starts out at 0 volts and then grows to 12 volts by 5 time constants, or 5 times 3 milliseconds, or 15 milliseconds. Given these functions, one could perform analysis of the transient period at specific points in time. Let's say we're being asked to solve for the instantaneous value of current through and voltage across the capacitor at time t equals 2 milliseconds. Note a time of 2 milliseconds would represent 2/3 of the 3 millisecond time constant. Substituting 2 milliseconds into the current through the capacitor as a function of time equation yields an instantaneous current value of roughly 30.8 milliamperes at t equals 2 milliseconds. Substituting 2 milliseconds into the voltage across the capacitor as a function of time equation yields an instantaneous voltage value of roughly 5.8 volts. Let's put these instantaneous values at t equals 2 milliseconds to the side for later use. One can also use these equations and plots to determine the time at which certain event occurs. For example, let's say we wish to know at what time the current spike has subsided to 10 milliamperes, 1/6 of its initial value. 10 milliamperes equals 60 milliamperes times e to the negative t over 3 milliseconds. What time value in milliseconds satisfies this condition? Divide both sides by 60 milliamperes. Take the natural log of both sides. Remove the negative signs on both sides of the equation and multiply both sides by the time constant tau. We're left with a time value of roughly 5.4 milliseconds. We can perform the same type of analysis for voltage. Let's say we wish to know at which time the voltage across the capacitor has grown to 10 volts, 5/6 of its final value. 10 volts equals 12 volts times 1 minus e to the negative t over 3 milliseconds. What time value satisfies this condition? Divide both sides by 12. Subtract 1 from both sides. Remove the negative signs from both sides. Take the natural log of both sides. Remove the negative signs on both sides of the equation and multiply both sides by the time constant tau. We are also left with a time value of roughly 5.4 milliseconds. Is this a coincidence? No, it is not. Current decays at the same rate voltage grows. Let's put these instantaneous values at t equals 5.4 milliseconds to the side for later use. Other electrical properties of interest can be calculated during the transient period, notably the current through the resistor as a function of time, IR of t, and the voltage across the resistor as a function of time, VR of t. Luckily, these properties are very easily obtained if you've got an understanding of series circuit properties, Ohm's law, and Kirchhoff's voltage law. The most fundamental property of series circuits is current through elements in series is the same. This means any current experienced by the capacitor is likewise experienced by the resistor. The moment the switch closes at time t equals 0, the resistor also experiences a surge of 60 milliamperes of current, which decays to 0 amps by 15 milliseconds. Current through the resistor IR of t can therefore also be modeled as 60 milliamperes times e to the negative t over 3 milliseconds. IR of t equals IC of t because current through elements in series is the same. As our previous analyses of IC of t demonstrated, current through the resistor would also obtain a value of 30.8 milliamperes at t equals 2 milliseconds. It will have decayed to 10 milliamperes by roughly t equals 5.4 milliseconds, and will have ceased altogether by t equals 15 milliseconds. Voltage across the resistor as a function of time can be calculated in one of two ways, either through the use of Ohm's law or Kirchhoff's voltage law. Importantly, both methods yield the same result, and the two methods can be used to check your work. As you are no doubt aware, Ohm's law states that the instantaneous voltage across a resistor is the instantaneous current through the resistor times its constant resistance value. V of R equals I of R times R. During the transient period, however, current is not a fixed constant value, but rather a time-variant expression. Therefore, voltage across the resistor will also be a function of time. VR of t equals IR of t times the constant resistance value R. Substituting in our given values, VR of t resolves itself into 60 milliamperes times e to the negative t over 3 milliseconds times 200 ohms, or 12 volts times e to the negative t over 3 milliseconds. Plotted as a function of time, VR of t looks identical to the plot of current as a function of time, only it starts at 12 volts and drops to 0 volts over a span of 15 milliseconds. Instantaneous voltage values across the resistor can be obtained by substituting the time of interest into this equation. Let's see if we can determine the instantaneous voltage across the resistor at t equals 0 milliseconds, t equals 2 milliseconds, and t equals 15 milliseconds, the end of the transient period. Substituting t equals 0 milliseconds into our equation demonstrates the resistor experiences a 12-volt drop. This makes perfect sense, because at t equals 0, current through the resistor, and every element in series with it, is 60 milliamperes. When 60 milliamperes flows through a 200 ohm resistor, it will experience a 12-volt drop. Substituting t equals 2 milliseconds into our equation demonstrates the resistor experiences a 6.2 volt drop. This also makes sense, given we previously demonstrated at time t equals 2 millisecond current through the resistor, and every element in series with it is 30.8 milliamperes. When 30.8 milliamperes flows through a 200 ohm resistor, it will experience a roughly 6.2 volt drop. Finally, substituting t equals 15 milliseconds, or 5 time constants, into our equation demonstrates the resistor experiences a 0 volt drop. This makes sense because at time t equals 15 milliseconds, current through the resistor, and every element in series with it is 0 milliamperes. Because 5 time constants into the analysis, the capacitor is fully charged, the transient period is over, and current flow has ceased. When 0 amps flows through a 200 ohm resistor, it will experience a 0 volt drop. Let's use Kirchhoff's voltage law at specific points in time to check our work. As you are no doubt aware, Kirchhoff's voltage law states that for every closed loop, the sum of voltage rises equals the sum of voltage drops. This holds true for continuous steady-state analysis as it does for the instantaneous transient analysis. Let's again examine this circuit at times t equals 0, 2 milliseconds, and 15 milliseconds. At time t equals 0, the Kirchhoff's voltage law equation for this series circuit is E equals VR plus VC. At time t equals 0, the capacitor is uncharged at 0 volts, and the resistor is experiencing the full 12 volt drop. The sum of voltage rises does indeed equal the sum of voltage drops. The Kirchhoff's voltage law equation for other moments in time remains unchanged. At all times, the rise E will be equal to the sum of instantaneous voltage drops, VR plus VC. At t equals 2 milliseconds, the resistor has experienced a 6.2 volt drop, and the capacitor has been charged up to 5.8 volts. 6.2 volts plus 5.8 volts does indeed equal a 12 volt rise. Does this or does this not make sense? It should. The source has induced a 12-volt rise for the complete series combination of two elements, and the resistor and capacitor drop their representative instantaneous portions of the complete 12-volt rise. Finally, at t equals 15 milliseconds, the capacitor is fully charged and current flow has ceased. All 12 volts is being dropped across the capacitor, and no voltage is being dropped across the resistor. The sum of voltage rises does again indeed equal the sum of voltage drops. If you think about it, the voltage across the capacitor as a function of time, Vc of t, is the mirror image of the voltage across the resistor as a function of time, Vr of t, reflected in a horizontal plane, and vice versa. If our instantaneous Kirchhoff's voltage law equation at all times is E equals Vr plus Vc, and Vr and Vc are in fact time-varying expressions, one can substitute these time-varying expressions into the Kirchhoff's voltage law equation as E equals Vr of t plus Vc of t. Our source, being a fixed constant value, in this case 12 volts, is not time-variant. We can use this Kirchhoff's voltage law expression to derive the voltage across the resistor as a function of time. If we know E equals Vr of t plus Vc of t, an algebraic rearrangement of the equation suggests that E minus Vc of t equals Vr of t. Substituting our given values, we obtain the expression 12 minus 12 times 1 minus e to the negative t over 3 milliseconds equals Vr of t. Simplifying this expression results in Vr of t to be 12 volts times e to the negative t over 3 milliseconds. Exactly the same expression we derived using Ohm's law, where Vr of t equals IR of t times R. In summary, Vr of t always equals IR of t times R, which always equals E minus Vc of t. You can use one method to check the other. Which method do I use? Ohm's law. It's simple and effective. This being said, I always check my work for instantaneous calculations using Kirchhoff's voltage law. Consider the occasion at roughly 5.4 milliseconds, when we know in fact voltage across the capacitor will have risen to 10 volts, and the current through this series circuit to be 10 milliamperes. I know, no complicated calculations necessary, that the instantaneous voltage across the resistor will be 12 volts minus 10 volts, or the remaining 2 volts, because the source has induced a 12-volt rise, of which 10 volts appears across the capacitor and 2 volts appears across the resistor. Ohm's law supports this conclusion. Given we demonstrated 10 milliamperes of current flows through this series circuit at this time, 10 milliamperes through a 200 ohm resistor will indeed result in a 2-volt drop.